All right, folks, let's get going here. Okay, folks, so we're just going to talk about the basic networking stuff, and if everybody's getting all the iClickers right, that'll be a clue that this is too easy, and we don't need to do these kind of reviews, but I'm imagining that may not happen. So the point of the OSI model is to make it possible for different manufacturers to make equipment and for it to interoperate. So you have to specify exactly what each layer is supposed to do. And there's two stacks. There's the OSI model, which is a European model and is mostly theoretical. And there's the TCP IP model, which is the way hardware is really built. And so the point of this is that you can now have a defined piece of network hardware like a switch or a router that does just one specified step of networking, and you don't have to solve all the problems in each device. That means you can have a switch from one vendor and a router from another vendor and a server from another vendor, and they'll all work together insofar as they all obey the standards. Unfortunately, nothing is perfect, and in fact, every device fails to really obey the standards completely, and there are a lot of mistakes in the standards. Nothing is ever complete at any level of this process. There's just something called RFCs, which are requests for comment, which means it's been approved by an IEEE committee, but there are endless revisions and changes and mistakes found in there. One of the most entertaining, egregious ones was Trivial File Transfer Protocol. Port 69 was published, and the official specification for Trivial File Transfer Protocol said, you send a packet, and every packet must have an acknowledgement. And if there's an error, you must send an error message, and that must have an acknowledgement. And the specifications as written said that if there's an error, you send an error message, which must be acknowledged, and the acknowledgement must be acknowledged, and it immediately floods the wire with ack, until nothing gets through, because they just made a mistake writing the rules. And this kind of thing happens fairly often. The huge DNS hack that Dan Kaminsky became famous for, when he testified before Congress, he could poison any DNS server on the internet, and the whole industry was vulnerable, not because of a bug, but because of the way the protocol was written. There was just a way to use it as written to poison the contents in a server, and they had to revise it. And those are the really awesome hacks, like SSL strip. SSL strip turns HTTPS into HTTP, which defeats all the security, and it does not involve a bug or a buffer overflow or anything like that you can patch. It's just a way to use the existing protocols in a way that completely destroys the security. And those are the really brilliant hacks that require you to think very deeply how to fix them. Anyway, so that's the game here. How many of you already seen this movie? Not very many. It might even be worth playing this movie then. Let me see if I got a local copy of it. Have you seen it? All right. Yeah, I think I'll do it at the end. I'll do it at the end. But that's fine. And then people can wander out if they don't care. But it's actually a fun movie if you've never seen it. It shows you how networking works from a Cisco point of view. What's that?
I hope they update it. That's pretty old.
No, it is pretty old, but it's still pretty good if you've never seen it. All right, so there's the OSI model, physical data link, network, transport. You number them from the bottom. And one of the many things that drives people nuts about this is that only the bottom four layers are real. There really is a difference between the physical. The physical is your wires, this is your Ethernet card, this is your IP addresses moving things through routers, and this is your TCP and UDP ports. And there is no actual distinction between the upper three layers. They're all just in your browser or email client. The original theoretical plan from Europe was that you would have separate software layers doing these, but in practice, these are all smushed into one thing. So up there, it gets sort of hard to define what the different layers are and which device is doing them and which software is doing them, because they're all sort of smashed together in reality. So there are mnemonics for it. Please do not throw sausage pizza away, where all people seem to need data processing. You have to memorize one of these. You want to pass exams and such. And there are protocol data units. At each, this is one thing that seemed crazy to me at first, and I got used to it, is every network packet has 3 addresses. This is also true of letters you mail through the mail. It has your name, it has the street, it has the city and the state and the zip code. There's actually many addresses at different scales on that letter, and that's what this is. So bits are the physical layer item. You're sending some kind of bits that go through some kind of medium like an Ethernet cable, and as far as the cable is concerned, there's no address or anything. Just bits are flowing through from one end to the other. It doesn't have any intelligence at all. That's the protocol unit here is bits. Frames are at the Ethernet layer, layer 2. That's the name of the data unit that moves, addressed by MAC addresses. And packets is the name of the IP layer, which is where things take large hops across the earth to find the physical location of the destination computer, even if it's far away. And once you reach the destination computer, segments at layer 4 are labeled with port numbers that tell you which process on the destination computer you want to talk to. And above that, they don't have protocol data units because, like I say, above that, they're more theoretical than real. But the first 4 layers are really real and really matter. Yeah?
Is this the segment one, is it the transport where it puts all the, when it's segmented, it puts back together?
Yes, absolutely. So
That's why we call it segment.
it is. That's why I'm glad you bring it up. So if I have something up here, like an email I write, and the email is maybe 10 kilobytes big, at this layer, it is broken up into 1,500 byte segments and addressed with, and then passed down to the other layers. That's where you break it up into chunks, and then when you receive it, this is where it's reassembled back into the original form so the higher levels can see one object. Exactly. All right. So that's what I've just done here, cables, switches, MAC addresses, and so on. And then service, your local area network is at layer 2, and the wide area network is at layer 3 that goes across the internet. And that's why I did quite a lot of layer 2 denial of service attacks, these IPv6 floods and such. And that's why, in general, one very common belief in the industry is that it's impossible to secure layer 2. There are so many attacks that to try anything at layer 2, what the most strong security you can have on layer 2 is to somehow lock the door and not let people get too close to your servers. Force them to come through the internet. If they can actually get into the room or connect on a port that puts them on the same layer 2 segment as your servers, then you're pretty helpless. And this is probably good security advice, but it's amazing how much people ignore it. I used to have a RapidZen cloud server, and I did a layer 2 scan, and I found that there were 178 other customers on the same layer 2 segment. And people have told me this is standard at data centers. You rent a server, they just put you in a virtual server on a rack with hundreds of other customers right there on the same layer 2. So any one of them could hack into or break down any of the others with layer 2 attacks. So this is one of the things about cloud security. An enormous number of people believe that somebody else is handling cloud security. There was a survey about a year ago where like 80% of people that put things in the cloud said, oh, security, the cloud provider is handling that. And when you read the cloud provider's terms of service, they all say, we give you no security, that is your job. And so people just take their existing data center, virtualize those machines, throw them on Amazon, and say, there, everything's fixed. And they don't realize they've just made themselves incredibly insecure because now it's all just public to the internet. Yeah?
Would the VLANs help security on the layer 2, or is it still pretty hackable if you're on the same switch?
That's a very good question because the answer is yes and no. And by the way, the answer is illuminating for how the security industry works. VLANs were invented by Cisco and put out there as a way to segment your network and advertised to the world as a security barrier. Then, very quickly, people found VLAN hopping hacks that went across, and then Cisco said, well, VLANs were never intended to be a security barrier. Now, this is what everyone always says. They sell you a lock, and then when they run a picture, they say, oh, well, that lock was just an ornament. That wasn't really supposed to stop anybody. And so VLANs do segment traffic and protect you from some attacks, but they're pretty weak, and it's pretty easy to hop from one VLAN to another. So
it's only meant to separate your traffic.
Yeah, and they are therefore a barrier of sorts. And this is really the case with every barrier. Your password, your encryption, everything is not perfect. It just stops some attackers, and there are people like the Equation Group that laugh at everything and blast right through, and there's nothing you can buy that will stop them.
So you'd have to have separate switches going to the router, and
if you had,
it'd be a little bit more secure.
yeah, physical separation would be more secure. Yeah.
But in the same router, you still have vulnerability.
That's right. And there's no perfection anywhere. But you can, that's why you have to have a threat model where you decide what are you worried about and you block that. You can't block everything.
And you use like multi-layer too. I mean, you can't just be like, oh, we're going to throw a firewall.
Yeah, well, that's right.
Firewall won't help, right?
It could help. All these things could help in the right configuration, and multi-layers of security is better than one.
Isn't that what Cisco's supposed to go to? I heard on the radio or something that they're supposed to go with the virtual, or some certain people are firing their workers.
Yes. Cisco is now firing something like 20% of the staff as they move to software-defined networking, which is what everyone knew was coming for years. This actual buying a bunch of physical hardware and putting it in a rack is kind of over. Now everything is virtual, and you have virtual switches and virtual routers, and Cisco needs to move into that space, which they haven't been in too much. Anyway, so these layers are real, and you can see them, and Wireshark is the main tool to learn them. In Wireshark, you see right here, layer 1 with like bits on the wire, Ethernet at layer 2, IP at layer 3, TCP at layer 4, and then you just go up to layer 7, because like I say, 5, 6, and 7 are all really lumped together in reality. but Wireshark is the main tool you use to learn this stuff and play with it and see it in package. So I got a few iClicker questions. Let me start my software, which should be down here somewhere. There it is. All right. Choose, start. Neat. Okay. And let's see if I can make this big and also have the, there, that's probably pretty good compromise. All right. Oh, so first let me just see if they're working. Some of these might have dead batteries, so just press A or anything, and let's see, let me see how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 18 if everybody has one. 13. So press like A and press E to make sure your clicker's working. If any are,
it's working.
well, perhaps. But anyway, press like A, then move to E. You know, I just want you to make sure they're working, so not too many roll. Discover your battery's dead halfway through. And if batteries are dead, bring them to me. They've been sitting all summer, so a few batteries might be dead. No problems? All right, we're up to 14, that's 15, all right. I'm willing to believe they appear to be working. Okay, so let's go here. All right, which layer is the transport layer? What's that?
What was the mnemonic?
Yeah, well, you got to learn your mnemonics.
You flashed it so quick.
Yes. Well, you got to memorize your mnemonic. All right, I'm going to quit at 35, I guess. Looks like most of the answers are in. All right, and that's layer 4. Please do not throw sausage pizza away. It's the T. So good, everyone knows that. Glad to hear. Or at least everyone who voted knows that. All right. All right, so let's try the next one here. All right, which layer has addresses like that? All right, looks like 25 will do for this one. All right, and that's layer 3, the IP layer. Not unanimous. But layer 3 is the internet layer where you use IP addresses like that. All right. How about this one? Where are the frames? All right, I'll quit at 25. All right, that's layer 2, Ethernet frames. All right. All right, at what layer do the signals go through the cable? All right, 25 will do. All right, and that's layer 1, the physical layer. All right. Where's the session layer? I'll quit at 25. All right, that's a higher order layer down there. I think it's 5 or 6. Sausage pizza way. 5, all right. But this is kind of intentional that I blur the others together because that's the way they really are. All right. How about that? Where do you find addresses like that? Putting at 25. That's not 128 bits, that's 48 bits. Each one of these is 1 byte, and you got 6 of them. So that's a MAC address for layer 2. 128 bits is a lot longer.
That's 48 bytes?
That's 48 bits.
6 bits.
Because each hex character is 4 bits. 2 of these is a byte, and you have 6 of them, so it's 48 bits.
Okay, I was
Yeah.
counting wrong.
Yeah. All right. Now, what layer has addresses like that?
Oh, yeah, okay.
2 bits. 1 byte in each 2 characters. I guess I'll wait till 30 on this one. Yeah, a nibble. Each character is a nibble.
Okay, that's right.
Yeah. All right. Now that is an IP version 6 address, so it's at layer 3. And this is the one that's 128 bits long. Each one of these has 16 bits, and there's 4 of them here for 64, and there's 1 here plus a hidden 3 of them, because the colon means it's all zeros in there. So this is 128 bits. So it's worth mentioning, that's what 128 bits look like, that's what 48 bits looks like. Anyway, all right. So let's try another. What layer is the internet layer? Well, I'm going to quit at 25, and I'm afraid I'm not going to grade this one. That's a kind of stupid question.
Yeah,
That's the other stack.
the different ones.
It is. And I think, I don't know what idiot wrote these questions. The problem is, there's none of them in the OSI model called the internet layer.
Yeah.
So you could argue the right answer is layer 3 because it's really the network layer, or you could argue the right answer is E because that's the wrong name. So this is a stupid question, and I'm canceling it. So, because there's no way to have.
Come on.
They're both C and E. Nah, that's too cruel. I'm eliminating that question. Let's go on to this one. Which layer uses segments? I regard that as excessively pedantic. Even though I wrote it, but I wrote it a few years ago.
You should just put this online, like you record the video before the quiz, make that one segment, and then record the rest.
Yeah, this is being recorded now.
Network practice.
Anyway, so I'll quit at 25. For segments are layer 4, TCP segments. There you are, layer 4. All right. So that's the game there. Well, that's one thing about those. You can. All right. So let's carry on here. All right. So the physical layer. You got bits on the wire. They're actually represented as complicated things like upward and downward transitions and frequency changes and such. And in this layer, you've got the wiring standards. And you've got issues like synchronizing bits and start and stop bits. And multiplexing is a big issue, which is how you're going to combine many signals down the same wire. Because laying a wire is expensive, and once you've got one, usually you want to send multiple signals down it. So there's the standard wiring convention here. The wires have to be in a certain pattern on one end and another pattern on the other end of your cables. So there's 8 wires in Ethernet. There is 4 pairs. There are 2 pairs for sending and 2 pairs for receiving, except for gigabit Ethernet that uses all 4 of them in a much more complicated way. Actually, I think only 1 pair is used for sending and 1 pair receiving, and 4 wires are not used in 100 megabit per second Ethernet. But in gigabit, they're all used. Anyway, so there's 2 general types of communication, synchronous and asynchronous. In synchronous communication, it's all synchronized by a clock. So a certain bit should come in at every tick, and you have to have one side sending a clock signal down, and that's serial connections. But the more common is asynchronous, where you send something down the wire, and you don't care how long the wire is or how long it takes to get there. It's a unified item. So this means it has to have some start bits that tell it a message is starting, and some stop bits to tell it a message is ending, because it does not have a clock signal to tell it when the bits are coming in. Those are the 2 ways to do it. You can also have broadband and baseband. If you have something like a radio transmission, like Wi-Fi, it's broadband, which means you have a variety of bandwidths available, and each one gets some region of the channels. But a baseband is like Ethernet, where the entire wire is used for one transmission, and you have all the frequencies from 0 up to the maximum available for use. What's up there? You got a question?
I was just curious, what asynchronous means you're not using a hardware clock or
Yeah.
So how do you measure speed?
you set the speed, which is how much distance it expects between the bits at the other end. And most modern, like Ethernet switches, do multiple speeds, and they're usually set to auto sensing, which means that if some clown sends 10 megabit per second, it'll slow them down. But they expect a packet to come in at a certain rate, and they wait to see when they have start bits, and then they know one's coming in. And they can deal with quite a bit of flexibility in the timing there. Anyway, so that's the game here, baseband and broadband. So time division multiplexing is one way to do it, and this is how phone calls typically go on T1 lines, or at least they used to. You would just have signals coming in on 3 wires, and you would just specify the first time slot is A, the next one is B, the next one is C, here's the next bit of A, B is not sending, here's the next bit of C, and so on. You just cut it with a clock, little pieces of time go to each signal, and this is how multiple signals can share the wire. This is, of course, kind of inefficient, because you see B was not sending a couple times, and those time intervals were just not used. So that's kind of foolish. So a better technique is statistical time division multiplexing, where it can somehow change how many slots it gives one channel if it's talking, and not give as many channels to the other, not give as many time slots to the other channel that's not talking as much. Yeah?
Well, wouldn't frequency division multiplexing be a lot more easier?
Yes, and much more efficient, but you have to have a multi-frequency cable. Yeah, we're getting, exactly. So frequency division multiplexing is the next step up. This is what you do if you have something like fiber optics. Or I believe the same thing's true of cable modem cable. But fiber optics, I know it's true. You can send multiple colors of light, and they won't interfere with each other at all. So you can send blue through, and if you send green through, it won't slow down the blue at all or mess with it at all, because you split them up with a prism or a diffraction gradient at the other end, and they go totally separate. So now you can just send multiple signals through and increase the total bandwidth, because each one of them can just send the full bandwidth, as much data as possible through, and the next one can send it right through the same wire with no interference. Yeah?
I saw an article trying to use quantum spin or something on there.
Yes, yes. The new thing that's coming out is they make more complicated fibers, and now you have rotational angular momentum to have another degree of freedom, but that's very exotic and not in common use yet. Right now they just have prototypes that only go like 6 kilometers.
That means all new hardware.
And you need all new cables. The cable has to have an air hole. Your cable has to have an air hole in the center, which fouls everything. Yeah. So that might be the next generation, but the current generation, this is what you do. You lay single mode fiber, and you run multiple divisions through it, and with dense wavelength division multiplexing, which is what phone companies use for, say, intercontinental traffic, you have something like 100 different frequency channels going through the same cable. And that's what happens is the fiber is the same anyway, but the NICs at each end get really expensive, like $10,000 to do this. All right, so that's layer 1 devices. You got cables, of course, for wired networking. You got wireless access points. You got hubs. Hubs are layer 1 devices. They're not very commonly used anymore. Hubs were the original thing used by Ethernet back in the old days. And hubs are completely stupid devices that any signal that comes in on any port is just echoed out all the other ports. So they're easy, but the effect is if we have this room layered with like 10 megabit per second Ethernet and a hub, then only one device in the whole room can send or receive at a time. Whereas if it was a switch at layer 2, they could all be sending and receiving at the same time. So you get an enormous improvement in bandwidth, and that has led to hubs being essentially extinct, because for the same price you could just replace it with a switch and get much better performance. But wireless Ethernet still works the way hubs work. If machines are here connected wirelessly, only one machine in the room can send or receive at a time, because there's no way to stop the signal from leaking all over the place by the nature of the radio. So it ends up adding up to essentially the same thing as a hub. And that's why wireless networks are extremely inefficient. You only get half the bandwidth to actually move data, because it spends a lot of time saying, shut up, I'm talking, somebody talked on top of me, clear the signal. Every single frame has to have an explicit acknowledgement at layer 2, because there's a very high chance that it gets corrupted before it gets to the destination. So, wireless is convenient, but very inefficient compared to wired networking. That's why when I'm doing CTFs and stuff, and I'm connecting to some server and it keeps kicking me off, I've learned to pretty much always use wired connection for CTFs, because very often the wireless connection is too flaky to really perform when you're trying to hack into things. So the data link layer is the next step up. Technically, it's split into 2 layers. There's a MAC layer, which has the addressing, the Ethernet address and such, and then there's a lower layer called the logical link control. But most people are content to just regard it all as the unitary layer 2. So if you do ipconfig/all, you will see your physical address, which is this 48-bit number expressed as 6 hexadecimal numbers. With 2 hex goes from 0 to F. Each one of these is 4 bits called a nibble. 2 nibbles make a byte, and you have 6 bytes. And there is no particular convention as to how you separate them. Some people use colons, some people use dag. It doesn't really matter. All right, so there's flow control here, which will prevent the sender from sending data too fast when the receiver can't handle it. There's error control. At Ethernet, there's a checksum. The checksum is a 32-bit CRC number. Now, this is used frequently in capture the flag contests and such because it's trivial to hack into. 32 bits, there are only 4 billion possible numbers. So a 32-bit hash is not enough to give you any real confidence that you're protected from an intelligent attacker. And there is, in fact, one of the latest scandals that came out again last week was the developers of Tor are using GPG, which uses public key encryption with a key of 1024 or 2048 bits, which is essentially perfect and uncrackable. But when they publish their key on a public key server, someone could put up a fake key with your name on it. So how do they know if it's the real key? And the answer is you put someplace, like on your business card, the hash of your key. So people can compare it. And people were using 32-bit hashes for that. So you could pretty easily make 4 billion keys until you get one with the same hash, put it up with their name on it, and people will think they've proven it's the real key by comparing that 32-bit hash. So this kind of hash, cyclical redundancy check, dates from decades ago when it was not true that you could easily do 4 billion calculations, and also it was never intended to stop an intelligent attacker. It was just intended to detect accidental bits lost on the wire from electrical interference or something. So if 1 or 2 bits flip, the CRC will change, and that's what it's there for. But an intelligent attacker can easily defeat anything as short as a 32-bit hash. That's a thing to be aware of. Anyway, this is also why you need something like Scapy or Wireshark, because if you just try to build packets yourself by writing C code, it will be annoying because you can't record packets and then change something like an IP address without recalculating the CRC. So be aware of that. It is an issue. Scapy automatically does that for you. Anyway, so that means at layer 2, every packet contains the data and it contains a hash. So when your receiver gets it, it calculates the hash. This is done inside your network card. And if the hash doesn't match, your network card discards the packet and does not pass it into your computer. It's thrown away and a retransmit is required. So there's error correction at layer 2. There must be, because it is well known that layer 1 is very risky, especially if it's wireless. Layer 1 has a large chance of dropping some bits, and so you have to automatically fix that, or you waste everybody's time up at the higher layers dealing with corrupted data. So switches and bridges and NICs all run at layer 2. A bridge was reformed to bridge 2 different networks together, and a switch is just a multi-port bridge. So, all right, and then you have the network layer. Layer 3, switching is not there, switching is in layer 2. This is routing. Routing is where you have a routing table and you have multiple directions. You could send them the data, several wires coming in, and you know what addresses are out each wire. So this is going to 10 dot something, it goes this way. This is going to 192.168, it goes that way, and on you go. Your router has to have a routing table listing all the addresses, and if it gets a packet going somewhere and it doesn't have an entry in the routing table, it either goes out the default route or it discards the packet, depending on how your router is configured. All right, so that's using your IP address. The MAC address is called a physical address because it's built into the ROM of the chip when it's NIC when it's manufactured. And although it can be changed in software, it's normally not changed. So if you move your computer to another place, the MAC address stays the same. It's tied to the physical object. The IP address is not tied to your computer at all. It specifies your physical location. And if you move to some other room, you get a different IP address because that's a different physical location. So that's called a logical address. It is not tied to your device at all. It specifies the environment of your device.
It's still true.
Yeah.
The MAC addresses that the first
Yeah.
3 they're the manufacturer, right?
Yeah, the first 3 specify the manufacturer, and the last 3 are just random, chosen by the manufacturer. And so you can totally tell what brand of device is out there, which is very handy. You can scan a network and find all the Macs, find all the Intel PCs, and so on. Yeah. All right, so packet switching is what happens at layer 3. There used to be just routing, but there's a thing called packet switching, which is just a faster way of routing, where you read only part of the address and switch. It's technically different. In practice, it's the same. It uses your IP address to determine where to go. Now, there are 3 kinds of switching. Packet switching is what's mainly used on the internet, where the data is broken up into packets with IP addresses, and every packet is routed independently. This is the modern system, because you can have many different signals going down the same wire. Each one of them has different addresses, and the router can handle them all without worrying about it. Circuit switching is the older system used by the analog phone network back when they had operators sitting in chairs with a bunch of wires and things to plug them in. So if you wanted to make a long distance phone call, you'd get a wire from here to England, and it was your 2 pieces of copper, and nobody else could use it as long as you were using it. So if you had 100 wires, you could have 100 calls, and that's it. You did not share the wires. Message switching is to handle things that are not always there, like email. If you send an email to somebody, their computer might be turned off. They might not log in until tomorrow. So message switching gives the message an address, like an email address, and it sits in a server waiting for someone to fetch it. There is no simple thing like routing. It's just waiting, storing forward. This is also being used for DTN, delay tolerant networking, which is a version of networking designed for spaceships. Now we're going to go to Jupiter and such. It might take 45 minutes for the light to get there, so you have this delay tolerant forwarding where you do not have any kind of, you're waiting for an acknowledgement or something. You just stick it in a box and wait until they're ready to receive it. So routers and these multi-layer switches work at this level. That's what Cisco calls them. They're very popular these days. That's a router on a stick in the Cisco terminology. All right, we got some more iClickers. So, all right, 23 telephones are connected to a line, so each one of them gets 1/23 of the total transmission speed. That's a T1. What is this? All right, I'll quit at 35, I guess. All right, that is time division multiplexing. The most popular answer, although that's where each one of them just gets a slot of time, whether they're using it or not. It simulates each one of them having their own wires, which was the idea.
Is that
Yeah.
the way POTS works?
What's that?
What's the example of the system that uses
T1.
T1.
T1 on copper did this. And it's still in use in some places, although again, mostly going over fiber now with a different system. All right, which one lets you add another signal to the shared line without slowing any other signal down? All right. I'm quitting at 25. I think the best answer here is FDM. I was thinking TDM you could argue, but anyway, FDM, and I'm glad nobody did that to give me a headache. Frequency division multiplexing, you can have a wire that was only intended to be used for 2 light frequencies, and then just add a third and it won't hurt anything. With FDM, if it was using only 2 and you made it 3, it would slow down. But if you had, say, 23 and you weren't using them all, you could take one that wasn't in use and use it without slowing it down. But anyway, FDM is the most logical answer. You can actually send more signal down the same wire, the same cable, without slowing anything down. All right, crossover cables, what layer are they? I guess I'll quit at 25. All right, they're layer 1, like anything else. They don't have any intelligence at all. All cables are layer 1. They just move electrical signals from physical properties. There is no addressing or thinking or anything. All right. Which one takes 10 physical wires to carry 10 phone calls? This was the original Edison system. Looks like I can quit at 25. All right, and that's circuit switching. You got a whole circuit that belongs to you. That's the way it should be. All right. All right. So which one works best when the destination device is unavailable, but it should become available later? quit at 25. All right, and that's message switching. You have a whole message that's delivered and waits somewhere for the recipient to decide they're ready to pick it up.
Are you recording all this?
Yeah.
Next semester's class will have all the.
Yeah, this cost, that's another, I'll deal with that later. All right, and in fact, okay, so I'm gonna stop this, and let's take a break. What's 5 minutes to 10? Let's come back at 5 minutes after 10. Gives you a 10-minute break, and I will stop this recording.
Are you just recording the audio on this, or are you recording?
Sound and the slides.
You, sir.
And so this is net 1. That'll do. All right.